Okay, so yes, paper is due on Thursday. Everybody remembers we are not having class on Thursday, right? Okay, get back to nodding and everybody's nodding. Okay, so instead you are having a project day. If you haven't started your project yet, bad. But if you wait until the last minute, you could utilize your class time to complete your project and get it emailed out to me. They should all be typed, they should all be 1 to 2 pages, all that good stuff, right? This is the civilization project, so you're looking at a region and talking about mathematics that was born in that area, basically. So what were they known for? Big accomplishments, okay?
What time do we need to have that to?
Let's just be nice and say midnight. I'm not going to put any time on it because the truth is I'm going to be flying to Arizona and time zone difference. I don't want to mess with it. So let's just say Thursday, 11:59 p.m. That'll work. All right, so that's what's there. And then you guys have a homework that's outstanding. The page 129, it's not due until the Thursday that we get back, and that's actually also another day that I'm not going to be here, right? I'm sorry. I know it's breaking y'all's hearts. I'm actually glad we're a little ahead in the notes because these two are going to tank my being ahead. So this guy is also going to be due on that day, so no class on 3/28, because that day I'm headed for Tarleton. Let's zoom in a little bit.
Oh,
Okay, so the 28th, no class that day also, so instead I'm just going to make these two homeworks due that day, and that'll be your participation or whatever for the day, and I'm not going to stress out about it, okay? So no class on 3/28. So that's what we got outstanding. Sound about right? I know y'all are going to be sad to miss me 2 Thursdays in a row. I can feel it in my heart.
Is there still going to be a video?
Yeah, so my plan is that I'll make a video that week sometime whenever I get back from spring break and post it with just a little bit of notes just so that we don't get completely behind. We're going to start on the Tuesday we get back from spring break, the move toward, what does it say? The move toward Europe or movement toward Europe or something like that in the book. So that's the next section. And then somewhere, when's y'all's test? Like 2 weeks after spring break? I don't have my thing. There's my thing. Let me look real fast. Let me look real fast. Yeah, it's week 11. So week 10, we're not going to be here on Thursday. So we'll just get a little bit of movement toward Europe in that week. And then on it'll be April 2nd, is the Tuesday of week 11. That'll be our review day. And then the 4th will be our exam day. So you get a week, come back, get resituated, finish out all of this stuff with the Greeks and the Romans and the Arabs. We'll finish out all that. And then we'll start moving toward Europe, and then we'll take a test. Okay, so test number 2. April 4th, I think, is that Thursday.
Yeah.
Good.
The day is my interview.
Uh-oh. Do we need to work something else out?
No,
Come talk to me if you need help.
I'll just eat a cheeseburger and my dinner.
You'll be great. Study in advance.
Before the interview. They before interview.
I do it after.
Yeah, be
I'll do it
upset.
on my way here.
Be fueled up for the test.
President.
Yeah. Bring some cheese fries or something, I don't know. Cheese sticks, I don't know. It's got to have cheese in it, right? Okay, so the truth is that after test 2, we are downhill really fast. Okay, so that's week 11 is test 2 right here, and then we only go through week 16, and that includes finals, right? So there's just a little bit of more new material, 12, 13, 14, 15, or 14 new material, and then review and final. So we are going to be skating downhill quickly. We're over halfway. This is week 9. Yeah, 8/16 done. 1/2.
When does, registration open for us to, register for summer?
It depends on your classification. So grad students, I think, is during spring break or right after spring break. I don't remember the exact date, but grad students first, and then seniors, and then juniors, and that kind of thing. So they kind of gradually get you into it. I did send an email today. There are a few of you who have been asking me about summer having Math 301, the geometry class, so that you can get it out of the way, especially if you're in your internship or residency. I know a couple of people in Navarro have missed 301 because we've been offering it face-to-face and not in the distance ed thing, so that's why we're hitting it in the summer, even though I was like, it's going to be so much not fun, because I'm going to have to send stuff, manipulatives and things, because this class is not a manipulative-based class, really, but the geometry really is. So we'll get those sent out, and that'll be summer 1. So I sent an email today. And if you're missing the 372, because that class didn't make this semester, there were 4 or 5 people that were in there, and they're kind of upset, because this first time ever it's not made. We're offering it online in the summer. So, and I think the reason it didn't make this spring is because I had 24 students in the fall in the online section. So we're rearranging the way we're doing some of that. But so it won't be offered again until spring. So if you need 372, get it this summer. And enroll early.
Do you know if it's summer 1 or 2?
Summer 1, it's Monday through Thursday, 11 a.m. Yep, fun stuff. 372 is online, or summer 1. So they're both summer 1, but the 301's face-to-face. It'll be so much fun. You're done with math after this? Congratulations. Yay. Almost ready to graduate. That'll be great. Okay, so tonight we're going to wrap up the Arabs. There's actually 2 guys in particular we need to talk about. So before we do that, we're going to, I'm going to give you one question to see if you remember what we talked about the last class period. So I want you to work on that, and we'll think about whether this could be your quiz question. Let's think about that. So we have a Diophantine equations, set of Diophantine equations. Remember we talked about that last time? And what we know is that there are 4 numbers such that the sums of any 3 are, I've got 27, 50, 49, and 45. Okay, so just a little practice to make sure you can do this. So find the 4 numbers, that's what we want you to do. If you need to, you can put it into a square kind of situation. $27, $50, $49, $45. Dig out your notes from the last class period if you don't remember. Get with a buddy if you weren't here. Mm-hmm.
So when you're doing that, are the do we just assume automatically that the numbers are in order?
It doesn't matter which ones you put where.
Okay, that's what.
First, second, third, fourth. I just go in order, but if you had said the fourth one is x minus 27, it won't matter.
I think this was confusing me. Okay.
Yeah. It's just the sum of any three, and so my first one might not be your first one.
Cool.
Hey there! They said you were on your way.
Did we determine last class that they all have to be positive?
I'm sorry, say it again?
Did we determine last class, like, our numbers that go, like, in the circles have to be positive?
They are all gonna be positive. Did I mess something up? I'm gonna set up the question.
I did this in my head, so hopefully I wrote it down, but hopefully when I did it in my head, it worked out.
It's really weird for it to be like outside in this class.
Welcome, time change.
Anybody else get fraction?
Fraction.
Y'all are making me nervous now.
Because I made up the wrong problem.
I figured out what I did.
Oh, I did, oh, okay, never mind. Nope. Nope. Okay, I got it.
They're making me nervous.
Wrong number.
Well, y'all know what happens when I make up a problem, right? Sometimes weird things. Oh, I'm off the page, dang it. All right, I think that the sum of everything is 57?
Yes.
All right, whew. Roberto got 57, he's nodding his head, yeah. All right, so if the sum of everything is 57, then it should be a pretty easy situation to come back up here and say, okay, 57 minus 27 is what?
30.
30 is one of my numbers, and 7 is one of my numbers, and 49, thank you. 8 is one of my numbers, and 12. All right, is that what I had? Yes, okay, I like it when we all get the same answer. All right, so that guy right there, for sure you'll see on test 2 in a few weeks. You get to take spring break off a bit and relax your brains, but don't let these things fall out of your brains, right? Because we got to come back 2 weeks after spring break and take a test. So, yay. Everyone remember that?
So it doesn't matter where you put these numbers, like in the bottom of the...
It doesn't. So, like here, if you were playing with this guy, because I know like Jeff was really messing with this picture, he likes it. So it doesn't matter. I put my 30 there. If you put your 7 there, I put my 7 here.
Yeah.
Put the 12 there, 8 there. You can put them wherever you want. Because when we add them in order of whatever, it's going to work out. So 30 plus 12 plus 8, those three will be 50. Right, which was one of my sums. But if you had your, say, 12 down here, then it'll be 30 plus 12 plus 8 is 50 for you down here. But it won't matter. You'll still get the same sums. So 12 and 8 is 20 plus 7, that's 27. That was that guy, right? And then 8 and 7 and 30, 38 plus 7 is 45. Okay, and then 7, 30, 49. Right? And if you put yours in different spots, it won't matter. You'll still have the same 4 sums. It'll just be in different locations, which is kind of what Brittany was asking. The order here just doesn't matter. which is kind of cool, right? It's not like a first place, second place, third place thing. It's just, these are my 4 numbers. All right? Yeah, that's awesome. Good job, guys. Or I should say primarily, ladies.
We get hundreds a day.
Hundreds for the day. Quiz grade. Something, something. We'll see how this plays out. People keep on trickling in on us.
Oh, no, there.
That's the quiz grade. There we go. All right, so I think that we were in the Arabs, and we kind of talked about the loveliness that is our Arabic numbers that we now use, and using the base 10 system, which is something that came around after the time of Christ, like around 500 AD. So we start using that. We start seeing 0 as a placeholder, all that good stuff. All comes to be because all the scholars ran away to the Arabians, right? Basically, trying to run for their lives. So we're still in the Arabs, but we're going to wrap them up tonight. And we have basically 2 guys that we want to talk about, so it's not too bad. And don't tell anybody, but if all goes well, we might get out early.
Never happens with you.
I know, it never happens normally, right? So we might. I think we could. I think it happens. Okay, so Al-Khwarizmi, that's the first guy. He is Arab. His dates are around 70, 80 to 850. They're not really certain about that. They've got a little bit of, we know he was alive in, like, say, 830. Okay, and we know he didn't do anything after about 850 whatever, so they kind of narrowed down his dates like that. But that's what they think are his dates. Okay, he is the one, the main one. He used the Hindu numbers, Hindu numerals, and that really came up with place value and 0. Okay, and the reason we know that is because he wrote a couple of books, and one of them in particular is called Algorithmy. Okay, that's an M. Me? Okay, so, which kind of really looks like the English word for algorithm. And what does algorithm mean? It's like, what? Okay, so there's an algorithm for how to solve an equation. There's an algorithm for how to put my shoes on in the morning. There's an algorithm for how I brush my teeth. My algorithm for brushing my teeth might be different than your algorithm, right? So the algorithm is just a way of doing things. That's what it is. So, and in general, we relate it to processes, and in very specific into computer processes, right? So whenever you write code, you write algorithms, which are ways to make the computer do things for you. Okay, so Algorithmy was a book that was published by Al-Khwarizmi, not to be confused. There's a lot of owls in this thing today, so just watch out. This one I think we can keep straight because Algorithmy sounds a lot like algorithm. Okay, it was his book. In it, he talks about adding and subtracting, and dividing and multiplying. He talks about halving, taking halves of something, and doubling. And he talks about square roots of stuff. Okay. And when I kind of look at those topics right there, I think, that's like lower level math in public schools today, right? Okay, so up until about the middle school, middle grades, we're learning how to add and subtract and multiply and divide, and we're taking square roots and stuff like that. So it's kind of like almost a teaching book for how to do these things, if that makes sense. But the coolness of it is that he's using the Arabic numbers. And so we see how he did those things using our new number system, right? Come on in. Okay, so we see how he's doing these things. He has this, he's the one that puts into place the idea of nothing. Okay. Which we know is, 0 is a placeholder, right, basically. There's nothing there. When you have nothing in that placeholder, you don't just leave it blank, you put in a 0 to hold the position, basically. And so that's the reason why we have, like, say, the number 103 instead of it looking like 13, right? So if we were in the Babylonian times, they might have had a hard time distinguishing between these, but Al-Khwarizmi is the one who goes, no, that's the ones position, that's the tens position, that's the hundreds position. There's not any 10, so we're going to put a placeholder, make it a 0. Okay, it's really kind of smart of him. Okay, in his algorithmy book, he talks about astronomy. He talks about the calendars and geometry. Okay. He also takes a little bit of time while he's talking about geometry, and he does maps of the world. And he uses our old friend Eratosthenes, the longitude and the latitude, right? So he does a really nice job of bringing together some of that stuff that Eratosthenes had done for longitude and latitude, and making these lovely maps of the world that has all that in there. So if you look up that book, Algorithmy, you can find copies of it around. And then he's the one that does a lot of that stuff with it. Okay. He was said to have said something like, we only need 0 and advanced thought. Okay, so it's kind of an interesting thing. He's like, we only need the 0. Once we have 0, then we just let our minds roam free, and we have advanced thought, and we can do all kinds of stuff. And he actually is the one who came up with, inside of some of his writings, the word for algebra that we use today. It's not quite the same, but I'm going to show it to you now. So he's the one that kind of took us from this arithmetic kind of world into, we're already kind of thinking algorithmically and thinking about algebra, to, we're going to do the algebra, and starts defining stuff. So in his writings, he has something that he calls the AL-JABR method. Algebra. The algebra method. Okay? Sounds a lot like algebra, right? Okay, and when they translate it into English, it will be algebra. So the algebra method is, he called it the method of restoration. Okay, and what he meant by that is, whenever I go to move something and I add something to one side of the equation, I'm going to add equal parts to both sides of the equation. So it's called adding equal parts to both sides of an equation. So restoration. Think of it as he's basically moving stuff from one side to the other. He's restoring it to the other side. So that's the algebra method, and I'll show you some of this in a second. No worries. And then he had another one that was called the and Mukabala is the best I can come up with. Mukabala. M-U-Q-A-B-A-L-A. M-U-Q-A-B-A-L-A. The Al-Mukabala method. Okay. And he called that his reduction method. Okay. And what does it mean to do reduction or to reduce something?
Subtracting equal parts of both sides of
not necessarily subtract, well, yeah, okay, so it will be subtraction, I'm gonna say subtracting and the idea being to reduce, okay, to make something smaller, okay? So in general, it's going to be a positive thing that I'm taking off, but it could be like a negative thing that I'm taking off, so you have to be a little bit careful about that. But his examples are all gonna be subtraction, so it'll work out nicely for us, okay? So this is the method of subtracting. And Lacey said equal parts, right? Equal quantities is what the book says. From both sides. Of an equation. Okay, so he would use relatively simple examples, but here's one. We have 3x plus 7 equals 8 minus x. Now this is actually very complicated for the time for what he's doing. Okay, so if we wanted to solve that guy, and that's where he's headed, solve for x, what could I do first? Okay, subtract a 7 from both sides. Everybody agree? Does that have to be your first step?
No.
Nope. You could have started with moving the x, right? So whichever side, whichever step you want, that's fine. Just the one I heard Darby say, so that's where we're going. Okay, so subtract a 7, and that would be, leave me with?
Or 0 on the left, so just
Okay.
3x.
0 pair from 372, 3x equals, what happens here? 1 minus x. Okay, so looking at that process, what we just did, is that algebra? Is that al-mukabala? Mukabala, right? Okay, so that's what he was doing there. Okay, so he said, oh, we can do these things, right? And then what?
The negative x to
Okay, so move that negative x over. How am I going to do that?
you add.
Add. By adding the same quantity to both sides. Okay, it goes away over here on the right. But I've got 3x plus x is 4x is equal to 1. So that guy, what step, what process is he doing, or what method? That's algebra, right? Okay. And so, and you have to remember that they're probably going to shy away from fractions. So at this point, they would say, okay, if you have 4 of those quantities, they're equal to 1. Okay. For us, we're probably going to take it that one extra step, and we're going to say, solve for x, and we're going to what? Divide both sides by 4. Yeah, this is a little, like I said, a little more advanced than what he was doing. He doesn't have, notice he doesn't have a name for that. Okay, we're a little farther along than what he had. And again, it's just because he's going to want to keep mostly positive whole number kind of answers going on for us. So that's what's happening. But he's the one who came up with, okay, in his algorithmy, the way of doing things, oh, if we're subtracting for both sides, we're going to call it the special name. If we're adding both sides, that's the same way of doing things over and over and over again. So he gets the credit for coming up with these processes. Okay?
How do you pronounce his own name?
Khwarizmi, yeah. So he actually, this book gets translated later, so thus algebra became translated to algebra, which we use to this day. Good for him, and it's all him. So on a test question, here you get special little nuggets today. On a test question, it might end up saying something like who gave the name basically for what we currently call algebra, right? And it would be Al-Khwarizmi. And I kind of keep that one straight because his name kind of sounds like the thing, right? Al-Khwarizmi, algebra. So he's got the A. He's the only Al guy that we have as a mathematician, so it'll pay off for us later. All right. Okay. So he's known for that. And then he actually did some applications with geometry. And this is where we're going to spend probably the chunk of time today. Okay, algebra applications with geometry. I know he said that I don't have to do that, but it makes me nervous. I've done enough of these recordings, and I'm like, stop it, don't do it. Okay, so applications with geometry. He had stuff like this: x squared plus 10x equals 39. And he said, how in the world are we going to solve that guy?
Does he set it equal to 0, like we do?
He does not. He actually, it could start out set equal to 0, and he actually ends up moving those constants over and setting them by themselves, which is kind of different. This isn't going to be solved with adding or subtracting, right? We're going to end up having to do some kind of something with that square, right? That square is messing us up. So, and we know today that because it has the square that it's going to end up with two solutions, right? X squared, it might be positive, negative, they could both be positive, they could be square roots, they could be imaginary numbers, right? These guys aren't working with imaginary numbers yet. They're just like, oh my gosh, what am I going to do about that? So some of the stuff that they work with is going to be almost pre-designated, like pre-set up, like almost a fate problem, if that makes sense. Like it's got to work just right, so they'll kind of set it up this way. So he actually comes in, he says, I'm going to use algebra. And we've seen instances where we had x squared before and we had to use algebra. What's that look like? What's an x squared going to look like? I'm sorry, in geometry. Did I say algebra? In geometry, they're like, it looks like x squared. In geometry, what's the x squared going to look like?
Oh, yeah,
Just gonna have to
Oh, the graph would look like that. But I mean in geometry. Geometry, when we're drawing pictures of stuff, and I say, hey, you, draw me a picture of x squared. You people who took 372 last semester. It's a square, right? Courtney's like, I don't want to say it. It sounds silly. You're right. It's a square, right? Okay, it's a square where I don't know the length, so it's x times x is x squared, and that ends up telling me the area of that square, right? That's what x squared means geometrically. It's like this picture, and we just know, I don't know the length, but I know that they're the same measurement, right? So it's definitely a square. Okay, so then what? What if he wanted to geometrically show me a picture of 10x? What's an x going to look like if this is x squared?
just a unit,
Just one unit?
right? Or is it just long?
It's the long, right? It kind of looks like a long, she's talking base 10 pieces, right? So it kind of looks like a long, it's x long because it's the same distance here, but it's only 1 unit wide, right? Because if I look at the area inside of this rectangle, it's x times 1, or 1x. Okay, so that's what an x looks like geometrically speaking. So this guy starts talking about, okay, I want to solve this if I have over here 39 little guys, and I'm not going to draw 39 little units, right? But if I had over here 39, these would be the units, right? This would be worth 1. Okay, so if I have all that over there, 39 of them, and he's like, okay, I need to solve this. I've got 10 x's over here. He's the one that first says, I got some x's here, and I got some x's here. And of course, he didn't have the lovely algebra tiles that we have nowadays, right? if you were in my 372 class. Okay, so that's 5 x's that I've got showing there, right? 1, 2, 3, 4, 5 of them, okay? So he said, oh, I don't know what the answer is there, but I can, and it's a really cool concept that we use today, and today we use it almost exclusively algebraically, but he used it geometrically. He said, let me complete the square. Okay. Completing the square. What does that mean for us in this picture?
Fill in until it's the perfect square.
It needs to be a perfect square, right? Okay, and so,
So we've got to add to it and take.
okay, I need 10 x's here. So how's that going to end up being? Now, a perfect square, when you say that, you mean that this distance here, whatever this length is going to be equal to whatever this total distance here ends up being. So I can add to both sides, but I got to have 10 of them, and I've only got 5. So what do we think about that? Like, I can play with it. If I add one here, that's 6. If I add one here, that's 7. I want them to be the same though, right? So I've got 4 here.
So if you add one to the bottom, you need
Okay. If I add one to the bottom, I need to add one to the top, right? So that's 8. 5 on the bottom and 5 on the side. Everybody agree? Okay. So that ends up making this thing be, okay, we're good here. Okay. It's going to look like, okay, cool. We're getting there.
And then you add 5 ones for each.
Oh, you want me to finish making it a square. Okay, so this is the part of the problem that was given to me, right? X squared plus 10x, I've just aligned them in such a way. And the reason he's got this 39 on the other side is he doesn't want it to confuse us. He doesn't want it to come into play. So it's just like, okay, ignore that number, who cares? Make a perfect square here, complete the square. So make it a square, and I heard Lacey say, in order to do that, in order to fill this in, you know, I need to
25.
fill in, yep, it's going to be a 5 by 5 square, right? It's 5 here and it's 5 there. Does everybody agree? Okay. And each of those little guys that fits in there is only this little bitty, I'm just going to shade one of them. Just this little bitty square here, right? There's 5 times 5 of those, or 25 of those. And what did we say that little bitty square was worth? 1. Okay. So what he's saying is, oh, if you want to complete that square, you need to add 25 little pieces there, right? So he's adding on 25 pieces here on the left-hand side to make this complete. Okay, but by his rules in algebra and al-mukabala, he knows what?
Do it on both sides.
I can't just do this on one side, right? If I just add 25 over there, it unbalances the equation. So whatever you add to one side, you have to add to the other. Okay? So now he's going, hey, look, this is a perfect square. Okay? I'm good there. This is all nice and pretty. And whatever that is, it's going to be equal to, okay, there was already a 39 there, add 25 to it. So 39 plus 25, it's going to be 14. Is that 64? Okay. What do we know about 64? It's a nice, pretty square, right? That's what I meant by some of these are just going to be very contrived. That's the word I was looking for. Very lined up for us, okay? And you're going to see that as you work some of them. So this guy, let me make him be written as a square. Whatever I did here on the left-hand side, that will end up being, it's a perfect square, right? So when I come here, it better look like something squared. So what's the length here? X plus 5, right? X plus 1, 2, 3, 4, 5. And whenever I go down the side, X plus 1, 2, 3, 4, 5. Okay, so this particular square is total X plus 5 times X plus 5. That's what that square is, right? So he's the one who kind of figured all this out. Oh, look at this, bless you. Okay, so now generally, when we see things that are being squared, it means this square has a length of x plus 5, and it's being squared. Okay, so I wrote right in the middle of that, I'm sorry. X plus 5 squared equals 64. From here on out, it's pretty straightforward. Remember, he already wrote about how to take square roots, so they should already know from their primary grades how to take square roots. So I've got this. X plus 5 squared equals 64, and what should I do? Square root of both sides. He didn't have a name for that. Like, got to be that we did it to both sides, right? just do it, yeah, I guess. Okay, so what happens on the left?
It's just x plus 5.
X plus 5 equals, okay, and they're only doing the positives because, again, geometric here, am I going to have a distance that's going to be the negative 5? You know, that negative 8? No. So anytime we take these square roots, my blue pen's running out of ink. Anytime I take these square roots, it's going to be an 8, a positive, and they just kind of ignore the negatives, which is why I said earlier, we know that this should have 2 solutions because it's x squared, right? But they're only coming up with whatever the positive solution is, so, yeah. All right, and then finally, we can, yeah, do some al-mukabai here and subtract your 5, and you get 3, okay? X equals 3. So that's his answer for that. So, and he would go back to the original, right, which was the x squared plus 10x, and he'd say, okay, let's plug in 3. 3 squared is 9, 10 times 3 is 30, and that better give me 39, and it does.
Is this where we get the little foiling square for, like algebra?
Oh, there is like a box method? Yeah. It's supposed to be, I don't know that it's necessarily from this, but it's supposed to be aligned with that kind of an idea. Yep. That you can do the multiplication through like that. Box method. Yep. Okay, so that's completing the square. Geometrically speaking. Now again, he would have had 39 little unit guys over here. He would have said, oh, I'm adding 25, so he would have added 25 to his 39, and he would have said, oh, there's 64 total, and then he would have gone from there. Okay, we're using our algebra skills because we know what they're equivalent to these days. That's so much fun, right?
Actually,
It's cool, right, that he thought of that geometrically first, and then now, whenever we tell kids nowadays complete the square, is there any geometry that really comes into it normally? No. We just throw them in, boom, here's the algebra, right? So let's talk about that algebra. Complete the square geometrically. I'm sorry, algebraically. I'm just stuck in my mixed here. Which one's geometry? Which one's algebra? They're all the same. I don't know why. All right, my problem is x squared plus 8x equals 9. Give yourself just a little bit of space before you do the equals 9. You might not have noticed I did that last time. X squared plus 8x equals 9. All right, so let's talk about algebra first, and then we'll come back and see what might have happened for him. Whenever we tell kids to do these completing the square things, there's like a 6-step process, an algorithm that we give them. Okay, so the first step is that you have to make a equals 1, right? Okay, now for this one and for the last one, they're both ax squared, right? The a is a 1 there. There's no constant number out in front, no coefficient, that's the word. Okay, that's the C word I'm after. So, but if it's not, then you have to make it be that. So in a little bit we'll work one that's not an A out in the front, but that's always step 1, make the A equal 1. Step 2 is move the constants to the other side. The other side. Okay. For the problems that he's giving me, they're going to already start out that way, right? He kind of sets them up in a very contrived manner. That's the best word I've got. Okay. So then step 3. This is where kids get lost, by the way. what exactly, and now we'll see where it's coming from, I hope. So what exactly is happening in here whenever we arrange those x's? We wanted it to be the same length here as it is here. Well, the x and the x are already the same length, so that means what for this 10x? How'd y'all know to throw it like this? Okay, good. We knew we had to have it on the bottom and on the side, so we split it by 2. So we agree with that? So we took whatever the b term was, for our algebra minds, whatever the b term was, and we divided it by 2, right? So b over 2 is what we tell kids. Take your b, divide it by 2, and then what did he do to it to figure out this red number that he had to add in? It was 10 divided by 2 is 5, right? 5 times 5, he figured out this has to be squared, right? Okay, so we have to square that guy. So b over 2 squared gets added to both sides, right? That's the third step in there. Depending on who's writing out the steps, number 4 is normally write the left-hand side as a perfect square. Okay, so I'm going to show you that. So take the b, divide by 2, square it, add that to both sides. That's what we did here. We added the 25. And then step 4 is write the left-hand side as a perfect square. So it's technically going to be a binomial that's going to be squared, right? If we did it correctly, that's what it's going to end up being. But this needs to be written as a perfect square. Now, does the right-hand side have to be a perfect square? No. A lot of times we end up with square roots and stuff like that. Now, this Al-Khwarizmi guy, he's never going to end up with, ooh, he lied to me. Kicked me off. You see that? So it's still recording though, so we're good. Okay, so he's never ever going to end up like that. He's always, with the square root, he's always going to set them up in just such a way so that they're going to be a perfect square. That makes sense? So, sorry, let me log in real quick. Knew it.
But it's still recording?
Yeah, it's still recording, but I'm going to have to. There, okay. It kicks me out and then I can't see what's going on over there. Okay. Alright, so he's always going to have something that works on both sides square, but ours is make sure the left-hand side is a square. And then what do we do? Okay, take the square root of both sides. Both sides. That's the algebra. And then the last thing that we did, the 6th step there, we took square root and then we solve for x, right? Okay, normally it's an addition or a subtraction step in there. Using your algebra or your al-mukabala, you'll do that. You'll remember that, won't you? Okay, so those are the 6 steps that we use nowadays, and it kind of makes sense why kids are like, oh, I can't keep these steps straight, right? There's 6 of them, okay? Even if you leave out the writing the left-hand side as a perfect square, there's still 5 steps there. It's still a lot. So without doing this geometrically, just algebraically, I'd like for you to take a second, follow our 6 steps, and see if you can solve that guy using completing the square. So just good old algebra. And I am going to stop the video and start a new one because we're getting close to the 1 hour mark.